When you look at the blueprints for a house, the plumbing system is usually pretty straightforward.
Yeah.
You have these narrow pipes bringing clean, pressurized water in, and you have wider, thicker pipes taking the waste out. It's purely passive. You flush, gravity does its thing, and the pipe just acts as a waiting room for the trash until it leaves the property.
Right. It's a very mechanical, lifeless process. I mean, the pipe itself doesn't fundamentally alter the waste, and the waste certainly doesn't generate electricity to power the plumbing.
Exactly. But imagine if you went down into your basement, cracked open that main waste pipe, and suddenly realized it wasn't just a chute at all.
Uh-huh.
What if you found out it was actually this highly sophisticated, densely populated chemical factory, and it was secretly generating the power to keep your entire house standing?
I mean, it would completely upend your understanding of how the house operates. And really, that is the exact paradigm shift we're talking about today when we look at the human body.
Yes. So, welcome to today's deep dive. We've pulled together a truly fascinating stack of sources for this one, ranging from original Renaissance anatomy illustrations all the way to cutting-edge modern gastroenterology journals.
It's a great mix of material.
It really is. And we designed this specifically for you, the curious learner who wants to cut through the noise, skip the dense jargon, and just get straight to the aha moments. So, okay, let's unpack this. Today, our mission is to radically change how you view your own gut, specifically the large intestine.
Which is so needed because for centuries, medical textbooks treated the large intestine exactly like that house plumbing we just described.
Just a dumb tube.
Exactly. It was viewed as an inert storage tube.
Oh.
But today, thanks to the explosion of microbiome science, we know that perspective is just completely obsolete. The large intestine is a highly active bioreactor. It's a microbial organ in its own right.
It's wild. And by the end of this deep dive, you're going to understand how your colon actually pulls massive amounts of water out of your waste, why it houses a microscopic ecosystem that rivals a rainforest, and my personal favorite from the sources, why a truly bizarre surgical fad from the early 1900s is still secretly influencing the modern wellness industry you see on your social media feeds today.
Oh, that surgical fad. It's quite the story. But to get there, though, we actually need to start by unlearning a massive misconception. And it starts with the very name of the organ itself.
Right, because I always thought large intestine meant it was the biggest, longest part of the digestive tract. But reading through these sources, that's just completely wrong, isn't it?
It's a classic misnomer.
Yeah.
Large absolutely does not mean long. The small intestine is this winding, twisting tube that measures roughly 6 to 7 meters in length,
Wow.
while the large intestine is only about 1.5 meters.
Wait, so the small intestine is 20 feet long, and the large intestine is only about 5 feet. It's 4 times shorter. How did it get the name large, then?
So it earns its name purely from its diameter.
Oh, okay.
Yeah, the lumen, which is the open space inside the tube, is about 6 to 7 centimeters across near its beginning. That is significantly wider than the small intestine, which is only about 2.5 to 3 centimeters across.
Got it.
And anatomists as far back as Galen in the 2nd century were distinguishing the gut segments by caliber.
Which makes sense, I guess, if you think about early anatomists just looking at a dissected body. You see a skinny, long tube and a short, fat tube.
Exactly. That visual distinction was heavily locked in during the Renaissance. Andreas Theselius published a massive work in 1543 called De Humani Corporis Fabrica, which gave us the first systematically illustrated human gut. From then on, the small versus large visual distinction just became the medical standard.
But the name isn't the only thing we get wrong. The functional misconception is even bigger. Because we call the whole thing the digestive tract, I always assume the large intestine is, in there cooking the meal and digesting our food right alongside the stomach.
It really isn't. By the time the partially digested food, which is called chyme, leaves the small intestine and crosses this one-way sphincter called the ileocecal valve into the colon, digestion is functionally over.
Over? Completely?
Pretty much. Roughly 90 to 95% of all your nutrients, so the carbohydrates, proteins, fats, and vitamins, have already been absorbed upstream.
So if it isn't the main chef, what is it doing? I like to think of the large intestine as the ultimate cleanup crew. The party is over, the guests have eaten, and the large intestine is stepping in to manage everything that the small intestine left behind.
That's a perfect analogy. What arrives in that first pouch of the large intestine called the cecum is essentially a slurry. It's a highly liquid mix of water, electrolytes, undigested plant fiber, dead cells that sloughed off the intestinal walls, and bacteria.
Yeah.
Right, very appetizing. But the colon's primary physiological job is to process that specific mixture.
Wait, so if the colon's main job isn't absorbing nutrients, what is it actually doing with that slurry?
Well, first and foremost, dramatic water recovery. If you look at the math of human digestion, it's really quite staggering. Every single day, roughly 9 liters of fluid pass through your gastrointestinal tract.
9 liters. I am definitely not drinking 9 liters of water a day. Where is all that extra fluid coming from?
Most of it is internal. You might drink and eat about 2 liters of fluid. The other 7 liters come from your own body's secretions.
Oh, like saliva.
Saliva, yeah. Plus gastric juices from your stomach, bile from your liver, and pancreatic juice. Your body is just constantly pouring fluid into the digestive tract to help break down food and move it along.
Okay, so 9 liters are flowing through the pipes. The small intestine absorbs the vast majority of it, right?
It does. By the time that fluid reaches the large intestine, there are only about 1.5 to 2 liters left.
Okay.
But the colon then absorbs nearly all of that remaining fluid. Out of those 2 liters, it typically leaves only about 100 to 200 milliliters to actually exit the body in your stool.
Wow, so it's doing a 90% water recovery job in the very last meter and a half of the digestive tract. But hold on. How does the fleshy tube pull that much water out of waste? It's not like it has hands wringing out a sponge.
No, it relies on a very elegant biological principle. Sodium drives water.
Sodium drives water.
Exactly. The cells lining the colon, called colonocytes, actively pump sodium ions out of the tube and into the body's tissues. They use specialized proteins for this, specifically epithelial sodium channels, or ENASI, and the sodium-potassium pump.
Time out. You just threw an acronym at me. ENAS.
Right.
Before we talk about how the water moves, explain what that channel actually looks like. Is it like a physical turnstile in the cell wall?
Think of ENAS as a highly selective, one-way microscopic pore embedded in the cell membrane that faces the inside of the intestine. It only lets sodium through.
Just sodium. Okay.
Yep. Once the sodium enters the cell, the sodium-potassium pump acts like a biological revolving door powered by ATP, which is cellular energy. It grabs that sodium and forces it out the other side of the cell back into your bloodstream.
So they're just aggressively bailing sodium overboard into the body. And because of osmosis, the water just naturally wants to follow the salt.
Precisely. By continuously moving the salt, the colon creates an osmotic gradient. The water has no choice but to follow the sodium back into your body, leaving the solid waste behind to be compacted.
But this system has limits, right? The cleanup crew can only mop the floor so fast. The sources mention that the colon has a ceiling of about 4 to 6 liters a day.
Right.
If you exceed that, you get diarrhea. And the sources brought up a terrifying example of what happens when that system is intentionally hijacked. Cholera.
Yeah, cholera is a masterclass in microbial sabotage. The cholera toxin doesn't just stop the colon from absorbing water, it actively forces the intestinal cells to open different channels and secrete massive amounts of chloride ions into the lumen.
Wait, into the lumen, so it reverses the whole process.
Exactly. The chloride gets dumped into the intestine, sodium follows it out, and then all the body's water rushes in to chase the salt. It completely overwhelms the colon's absorptive ceiling, producing a severe, life-threatening rice water diarrhea. It drains the body's fluids so rapidly it becomes deadly.
That's terrifying. But understanding that sodium drives water logic is also how we learned to fight back, right? Because this is the exact mechanism behind oral rehydration therapy, or ORT.
Yes, absolutely.
The World Health Organization recommends this simple sugar, salt, and water solution. You're basically giving the gut a massive dose of the exact chemical keys, the salt it needs to overpower the toxin and force water back into the body. And it saved tens of millions of lives.
It really is one of the most significant medical advances of the 20th century. ORT primarily works in the small intestine, but that same fundamental law of physics, water follows sodium, is how your large intestine keeps you hydrated every single day.
Okay, so the colon has drained the water out of the slurry, but that leaves a huge question. If the water is gone and the nutrients were absorbed upstream, why is there still so much physical mass left over? Like, what actually is the solid waste?
Well, it's mostly undigested plant fiber, dead cells, and microbes. Trillions of them. We really need to comprehend the staggering scale of this ecosystem.
Lay it on me.
A widely cited recalculation from 2016 put a total number of human cells in the average body at roughly 30 trillion.
Okay, 30 trillion human cells, making up the brain, the heart, the skin.
Right. But that same body houses roughly 39 trillion bacterial cells. And the overwhelming majority of those non-human cells live right in your large intestine.
That's insane.
We are talking about densities reaching 100 billion to 1 trillion organisms per single gram of colon contents.
That is wild. You are basically walking around with a microscopic, densely packed metropolis inside you. But they aren't just sitting there hitching a free ride, are they?
Not at all. Consider how digestion works upstream. Your small intestine couldn't break down dietary fiber. Things like cellulose from kale or resistant starch from cold potatoes. You just don't have the enzymes for it.
Right.
But these bacteria do. They actively ferment those indigestible carbohydrates.
So we eat the celery, we can't digest it, the bacteria feast on it, and that fermentation process creates a byproduct. What did the sources call it? Short-chain fatty acids.
Specifically, one major one called butyrate. And this is the great plot twist of human biology. Butyrate isn't just waste to the bacteria. It is primary fuel for you.
I love this. It's the ultimate symbiotic rent payment system. The bacteria live in your colon, you give them the fiber you can eat, they ferment it, and they pay their rent by feeding the landlord.
They feed the landlord substantially, too. Butyrate supplies an estimated 60 to 70% of the energy needs for your colonocytes, the very cells making up the lining of your large intestine.
Wow.
Your colon literally relies on bacterial waste products to survive, multiply, and maintain a healthy mucosal barrier.
So when you hear dietitians talking about a low-fiber diet being bad for you, it isn't just about digestion moving slowly. If you don't eat fiber, you aren't feeding the bacteria, which means the bacteria can't make butyrate, which means you are literally starving your own colon lining.
Exactly. And the anatomy of the colon is actually perfectly designed to facilitate this fermentation. It features these three longitudinal muscle bands called the tennae coli.
Wait, let's break that down. Tennae coli. What does that actually look like? Because the sources threw a lot of anatomical jargon around right there.
Sure. Think of the colon like a pair of sweatpants with an elastic waistband that's pulled a bit too tight.
Okay, I can picture that.
Those elastic bands running down the length of the fabric are the tennae coli. When those muscle bands contract and pull tight, the fabric of the colon bunches up into little pouches. We call those pouches haustra.
So by bunching up like sweatpants, it creates all these physical speed bumps.
Exactly. It traps the waste in these segments, churning it back and forth. This slows the transit time down tremendously, giving the bacteria enough time to thoroughly ferment the tough plant fiber.
And then, usually right after you eat a meal, the body clears the tracks. Something called the gastrocolic reflex kicks in.
Yep.
The stomach signals the colon, triggering these massive, sweeping muscle contractions called mass movements, which sweep that fermented, compacted mixture toward the rectum to be eliminated.
A brilliantly coordinated, highly evolved system.
But here's the thing. Today, we have the DNA sequencing to know that these bacteria are essential. But historically, our misunderstanding of this dense microbial jungle led to some of medicine's most unhinged mistakes.
Unhinged is definitely the right word. In the late 19th and early 20th centuries, doctors realized the colon was packed with bacteria. But bacteriology at the time was heavily focused on pathogens, germs that cause disease. So naturally, they assumed this massive bacterial colony sitting in the gut must be incredibly dangerous.
So they looked at the cleanup crew and assumed they were a toxic threat.
Exactly. Which brings us to Elie Metchnikoff. He was a brilliant scientist who shared a Nobel Prize in 1908. But later in his career, he developed the theory of autointoxication.
Autointoxication.
Yeah. He believed that putrefactive bacteria sitting in the large intestine were constantly producing toxins that seeped into the bloodstream, causing premature aging, arteriosclerosis, and even insanity.
The idea that you are literally poisoning yourself from the inside out just by digesting food.
Metchnikoff's proposed cure was to drink massive amounts of soured milk, modeled on the diets of long-lived Bulgarian peasants. He thought the lactic acid bacteria in the milk would colonize the gut and fight off the toxic bacteria.
And just to pause here for a second, this guy's slightly misguided theory about aging and sour milk is literally the birth of the modern yogurt and probiotic industry. Like the founder of Danone publicly credited Metchnikoff's ideas when he started selling yogurt as a health product in pharmacies in the 1920s.
It's pretty amazing. And yogurt is perfectly healthy, of course. But the core theory of autointoxication got taken to a much darker, much more radical extreme by a British surgeon named Sir William Arbuthnot Lane.
Oh, this guy. This part of the sources absolutely appalled me.
Yeah, Lane took Metchnikoff's idea and escalated it to a surgical level. He believed in a condition he called chronic intestinal stasis. The theory was that sluggish transit through the colon was allowing these toxic byproducts to steep and poison the body, causing everything from arthritis to depression.
Okay.
So starting in the early 1900s, his solution was to just remove the problem. He began performing subtotal colectomies.
Which means he was cutting out people's entire large intestines. And not because they had cancer or ruptured bowel, but just because they were constipated and he thought the organ was inherently toxic.
Right. He removed the colon entirely, essentially wiring the small intestine directly to the rectum. He performed or inspired thousands of these surgeries over 2 decades. Patients underwent major abdominal surgery with massive risks of infection and mortality, purely based on a theory.
It's the textbook definition of surgical overreach. Plausible-sounding physiological theory running miles ahead of actual evidence.
Definitely. Eventually, in the 1920s, the medical community caught up. The mounting surgical complications, the tragic deaths, and the absolute lack of supporting evidence finally discredited the practice. Mainstream medicine abandoned the idea that the colon was a toxic swamp.
Okay, but if doctors thoroughly discredited the idea of autointoxication 100 years ago, why on earth am I still seeing targeted ads on social media for detox teas and colon cleanses? They use the exact same language. They talk about flushing out toxic sludge that sits and rots in your gut.
It is fascinating how a scientifically dead theory can survive for a century as a cultural wellness myth. The commercial detox tea and colonic irrigation industry is the direct, unscientific descendant of Metchnikoff and Lane. Mainstream gastroenterology entirely rejects it.
Because, there is no rotting waste that needs external flushing. The cleanup crew is handling it.
Exactly. A functioning colon manages its own clearance. Intervening with aggressive external cleanses carries real medical risks. You can cause severe electrolyte imbalances, strip away the protective mucus layer, or even cause dangerous bowel perforations.
Jeez.
And it offers absolutely no demonstrated detoxification benefit. Your liver and kidneys handle detox. Your colon handles waste.
So if we definitely should not be aggressively flushing our colons out with detox teas, how is modern medicine treating the gut? It seems like the renaissance of microbiome science is all about learning how to replenish it, not empty it.
We're now looking at the large intestine as an ecosystem to be protected at all costs. And a perfect example of this changing perspective involves a tiny, attached organ that we have historically mocked, the appendix.
Ah, the ultimate evolutionary leftover, the tiny little tail on the cecum that you only ever think about when it gets inflamed and a surgeon has to yank it out.
Right. For most of the 20th century, it was taught as a completely functionless vestige. But in 2007, researchers at Duke University proposed a compelling new hypothesis. Based on its anatomy, it's a narrow, blind pouch situated just out of the main flow of the fecal stream. They suggested the appendix is actually a safe house.
A safe house for the bacteria.
Exactly. The idea is that it acts as a protected reservoir, sequestering a sample of your beneficial gut bacteria. So if you contract a severe diarrheal illness like cholera that flushes your colon out entirely, sweeping away your microbiome,
Oh, I see.
the bacteria hiding safely in the appendix can emerge to recolonize the large intestine once the infection passes.
That is such a great visual. It's like having an external hard drive backing up your microbiome. When a virus crashes your main computer and wipes all the data, the hard drive just plugs back in and restores the system.
That's exactly it. And while the exact mechanics are still being studied, it fundamentally shifts how we frame the anatomy. We are actively looking for the functional value of the microbiome. And the most undeniable proof that this microbial ecosystem is a load-bearing essential organ is a modern medical treatment called fecal microbiota transplantation, or FMT.
Okay, I know what those words mean individually, but put them together. We are talking about transplanting poop.
We are. Specifically, taking a highly screened, healthy microbial community from a donor and delivering it into a sick patient's colon. The FDA authorized FMT for a very specific, dire situation: recurrent Clostridioides difficile, or C. diff infections.
C. diff is a severe colon infection, and the issue is that it becomes dangerously resistant to antibiotics, right?
Think about how broad-spectrum antibiotics work. They're like dropping napalm on a forest. They kill the bad bacteria, but they also wipe out the good bacteria, leaving an empty, desolate landscape.
Right.
The problem is that C. diff can form hardy spores that survive the napalm. When the antibiotics stop, the C. diff wakes up, finds an empty colon with zero competition, and takes over completely.
So you try to bomb the bad bacteria, but they just keep coming back stronger. How does FMT fix that?
Through competitive exclusion. By performing FMT, you're essentially replanting a dense, incredibly diverse, healthy forest. When those trillions of donor bacteria take root, they consume all the resources and take up all the physical space on the colon wall.
And the bad stuff gets crowded out.
Exactly. The C. diff simply has no room and no food to grow. It gets choked out by a healthy ecosystem. Clinical trials have shown that for recurrent cases, FMT cure rates hit 85 to 90%.
That is incredible. It means that replacing the bacteria cures a severe disease that standard pharmaceutical drugs cannot. It is the ultimate proof that what we used to write off as a waste chute is actually a highly sophisticated, life-saving ecosystem.
It really proves the colon's bacterial community is not passive cargo. It's an active, essential organ system.
Man, this has been such a wild journey. We started by realizing that the large intestine is actually named for its width, not its length. We learned how microscopic cellular pumps act like biological revolving doors to recover our body's water. We found out that our colon cells pay their bills using butyrate generated by trillions of microbes, all while wearing anatomical
The
sweatpants.
sweatpants analogy is definitely going to stick with me.
Right, and we traced the history of how misunderstanding those bacteria led to extreme surgeries and how those debunked ideas still haunt the wellness industry today.
It really highlights how much our understanding of human biology has evolved, just by shifting our perspective from mechanical plumbing to ecological science.
But before we wrap up this deep dive, the sources mention one more thing that we barely scratched the surface of. It's something called the gut-brain axis, and honestly, it left me questioning a lot of things.
Yeah, that is perhaps the most profound implication of microbiome science. We know that the 39 trillion microbes down in your colon aren't just fermenting fiber. They're constantly churning out metabolites like short-chain fatty acids that enter your bloodstream.
Right.
And we now know that these chemicals can interact with your gut's enteric nervous system, which is often called the second brain,
hmm
and send signals directly to your central nervous system.
So they're literally altering neurological signaling.
We used to think the large intestine was just taking orders from the top. But if this dense, microscopic metropolis inside you is actively producing chemicals that can influence your mood, your stress levels, and even your cravings.
Wait, so the next time you have a sudden, unexplained shift in your mood or an intense craving for a specific food, it raises a fascinating question. Who is really in charge? Is it you? Or is it the microscopic ecosystem living in your large intestines?
Slightly unsettling thought, isn't it?
It really is something to ponder. Well, until next time, keep diving deep.